everyone. Myself Dr. Vijayakumar, Associate Professor, Department of Electronics and Communication Engineering, Aditya University. In today's session, we are going to learn about the spectral characteristics of the noise. At the end of this particular session, we will be able to learn two learning outcomes. One learning outcome is understanding the spectral characteristics of noise, and another one is understanding the properties of narrowband noise. So, the spectral characteristics of system response for noise. So, here we will apply a random noise signal LTI system, and the system modifies the noise spectrum according to the frequency response. So, the equation which is related to this statement is Sn naught of f is equal to absolute value of h of f whole square Sni of f. Sn naught of f is the power spectral density of output noise, Sni of f is the power spectral density of input noise, h of f is the system transfer function, Ni of t and N naught of t are the input and output noise respectively. So, when I apply a random noise signal to the system, so what happens is it will modify the noise spectrum according to the frequency response. So, the system shape the noise spectrum according to the frequency response magnitude squared. Noise that is present at the frequencies is also gets amplified, and noise outside the passband gets attenuated. Okay, this is the advantage of this system. So, let us take x of t is input applied to the system, y of t is the output obtained at the system. So, y of t is equal to x of t convolution of h of t. H of t is the system impulse response. H of t is nothing but system impulse response. If I apply Fourier transform on both sides, what happens? Y of f or y of omega is the Fourier transform of y of t, which is nothing but minus infinity to infinity y of t e power minus j omega t dt. So, applying Fourier transform on both sides, the expression will be y of omega is equal to h of omega into x of omega. H of omega is equal to y of omega by x of omega, which is equal to transfer function of the system. The transform of the output by the transform of the input is nothing but transfer function of the system. Okay. H of f is equal to y of f by x of f. H of s is nothing but transfer function. Omega is equal to 2 pi f. Sometimes we represent with omega, sometimes we represent with f. So, y of omega is equal to h of omega into x of omega. Okay. If I consider a wide-sense stationary random process, so the power spectral density by limiting the average of squared magnitudes to a finite Fourier transform. So, considering the narrow band wide-sense stationary random process concerning the noise. So, we know that the power spectral density is mathematically defined as Sxx of omega is equal to limit t tends to infinity 1 by t expectation of xt of omega whole square. In place of omega, I replaced it with f. Sxx of f is equal to limit t tends to infinity 1 by t expectation of absolute value of xt of f whole square. And output power spectral density also mathematically defined as limit t tends to infinity 1 by t expectation of yt of f whole square. So, this is the block h of f, and this is x of f, this is y of f, and the power spectral density corresponding to output is sy of f, power spectral density corresponding to the input is sxx of. So, using the mathematical definition of power spectral density, we have deduced these expressions sxx of f and sy of f, and we know that the relationship between output and input in frequency domain is given by y of f is equal to h of f into x of f. Convolution in time domain is mathematically equal to multiplication in frequency domain. Here the output is multiplied with the finite spectrum h of f. So, the output is nothing but the multiplied version of input signal with a finite spectrum h of f. So, replacing y of f with x of f into h of f, what happens? Let us see. So, here y of f whole square. So, replacing this, y of f is equal to h of f into xt of f whole square. I am bringing outside h of f whole square. Now, this is nothing but limit t tends to infinity 1 by t expectation of absolute value of xt of f whole square. So this is mathematically equal to Sxx of f. So the output power spectral density is nothing but absolute value of transfer function whole square into input power spectral density. More specifically, the output noise power spectral density is equal to the magnitude square of transfer function whole square into input noise power spectral density. This is the relation which gives us, which tells that if a system is multiplied with a input spectrum by h of f, the power spectral density involves the squared magnitude of spectrum, so that the output power spectral density is equal to input power spectral density multiplied with h of f whole square. So if it is simply a function, system function y of f is equal to h of f into x of f. When it comes to noise power spectral density, sy of f is equal to absolute value of h of f whole square into sxx of f. According to this spectrum, the output noise gets modified. Based on the shape of this spectrum, the output noise also gets modified. Some noise is added into the system. If the noise is present in this spectrum, that will get amplified, and the noise which is present outside the spectrum, that will be completely attenuated. So inside the spectrum, the noise will be amplified. Here it will take amplification, whereas outside spectrum, we can see the attenuation. So inside it is getting multiplied. So clearly the shape will be modified. So we can see here, what is the conclusion we can make from this one is, the output power spectral density is equal to absolute value of h of f whole square into sx of x. So the noise power spectral density is shaped by the system power gain. So the noise power spectral density is decided by the system power gain. Here there are three different cases we need to observe here. The first case is the frequency band, which is where h of f is high, the noise will get amplified. And the frequencies where h of f is, absolute value of h of f is nothing but system gain or power gain. If it is low, the noise will be attenuated, the noise will be less. And if the frequencies outside the passband nearly have zero noise, the output noise gets amplified if h of f, absolute value of h of f is more. So absolute value of h of f whole square decides whether output noise is amplified or output noise is attenuated. It depends upon h of f, and h of f is high, it is amplified, h of f is low, it is attenuated. If the band of the noise is outside the frequency band, we don't see any noise in the output spectrum. So the output noise power can be related with output noise power spectral density. We know that the power spectral density is nothing but noise per bandwidth. So how do you get noise? Noise is equal to power spectral density into bandwidth. Noise is nothing but power spectral density into bandwidth. Using this relation, the noise, output noise power can be computed as integrating the output power spectral density with respect to df. This df is nothing but bandwidth. So we know that sy of f can be written as absolute value of h of f whole square into sxx of f. This tells us how much noise power is going to reach at the output. So here, what is the noise, output noise power getting at the output side can be obtained or can be mathematically calculated using this relation. For example, I am applying a white noise power spectral density as an input and the output, let us say sy of f. We know that the white noise power spectral density is constant for all frequencies. So a white noise consists of all frequency components minus infinity to plus infinity. So this is nothing but white noise power spectral density. Sxx of f is equal to n0 by 2. So if it is applied as a input to a system, the output is equal to n0 by 2 into absolute value of h of f whole square. We know the relation, sy of f is equal to absolute value of h of f whole square into sx of f. So the input noise gets multiplied with the magnitude squared of transfer function. The system shape of flat noise spectrum is multiplied with the system transfer function shape. So the output spectrum depends upon the h of f spectrum. So both gets multiplied and the output spectrum shape is decided by the multiplication factor. Let us take an ideal low pass filter, in particular an ideal low pass filter. We know that the ideal low pass filter is mathematically or graphically represented as absolute value of h of f is equal to 1 over the band minus fc2 plus fc. Let us say this as minus b or plus b. So, absolute value of h of f is equal to 1 when f is less than b. That means minus b to b. Now, let us apply the input Sx of f is equal to n naught by 2. Now, what is the formula? Sy of f is equal to absolute value of h of f whole square into Sx of f. So, what is h of f? 1 square into n naught by 2. So, the output power spectral density is n naught by 2, but it is band limited, because who is going to limit the band here? The filter frequency response is defined only over a predefined bandwidth, whereas input power spectral density is defined for entire frequency range which lasts from minus infinity to plus infinity. So, the output power spectral density when white noise is passed through a low pass filter is nothing but n naught by 2, and it is restricted to frequencies from minus b to plus b. And if you want to compute the output noise power, we know that the output noise power is nothing but minus infinity to infinity Sy into df. Here Sy is n naught by 2, df is 2b, n naught by 2 into 2b, n naught into b. So, the output noise power is nothing but n naught into b. Okay, output noise power and output noise power spectral density we calculated when a white noise is passed through a low pass filter, and we have chosen the low pass filter as an ideal low pass filter. So, the output noise we got n naught b, and the output noise power spectral density we got n naught by 2 over the range absolute value of f less than b. Next one is narrow band noise. Narrow band noise is nothing but a narrow band noise is a random noise where the power spectral density is concentrated very near or very close to carrier frequency. Rather than spreading over a wide frequency range, the noise is concentrated around the carrier frequency, very much close to carrier frequency. So, that is why it is called narrow band noise. If it is expanded over a central frequency or a carrier frequency, we call it as wide band noise. It is usually the type of noise which is found in band pass communication systems. Particularly in radio receivers, we use the band pass filters. So, in the band pass filters, we use this, we see this effect, narrow band noise. So, a narrow band noise can be mathematically expressed as n of t is equal to nc of t cos 2 pi f ct minus ns of t sin 2 pi f ct, where nc of t is the in phase component of the baseband noise and ns of t is the quadrature phase of the baseband noise. If you take any noise, if it is split into parts like in phase component and quadrature phase component, the expression can be written something like this, where NC of t and NS of t are the low pass centered around the 0 and contains the envelope information of narrowband noise. The amplitude information, envelope information is available in NC of t, but when we are expressed as in phase, we will express as NC of t cos 2 pi f ct, NS of t 2 pi f of t. There are few properties for narrowband noise. When NC of t and NS of t are jointly Gaussian random process, if NC of t and NS of t will be jointly Gaussian, provided if N of t is completely Gaussian, the in phase component and quadrature phase components also will be a Gaussian noises. And similarly, if there is a zero mean in the total noise, then the mean of in phase component and quadrature phase component will be 0, and equal power in the sense in phase E of x square will be same for in phase component and quadrature phase component. When do we say two components are uncorrelated in narrowband noise? Means if in phase and quadrature phase component, if you compute the expectation of xy is equal to 0 indicates they are uncorrelated. And envelope and phase can be calculated using the formula. The envelope is nothing but the magnitude absolute value of or square root of nc square of t plus ns square of t, and phase can be computed as tan inverse y by x. So that is ns of t by nc of x. X plus iy, the magnitude will be root of x square plus y square. This is nothing but envelope, and the phase will be tan inverse y by x. So in the earlier slide, we expressed noise as a summation of in-phase component and quadrature phase component. The magnitude and phase can be computed using this formula. And the power spectral density relation, power spectral density of NC of t and NS of t are identical. Both will have equal, okay, both the noise power will be shared equally over this band of components. Next, quadrature phase representation of a narrowband noise. So when we express the noise in terms of complex envelope form, noise can be expressed as a n of t e power j 2 pi f c t. As per Euler's relation, this can be expressed as nc of t plus j ns of t. This is nothing but the complex envelope of analytical signal. The complex envelope analysis is useful in the communication system to convert the band pass signals into its equivalent low pass representations. There we use the concept of this complex analysis. Okay. So this is nothing but narrowband noise representation. This is the quadrature representation of narrowband noise. The mathematical expressions can be represented like this. So in this session, what we have learned is, firstly we started with spectral characteristics of system response for noise, and we deduced the relation Sy of f is equal to absolute value of h of f whole square into Sx of f, which tells that the noise will be shaped based on the spectral factor. And also we defined what is meant by narrowband noise, and also we have seen the properties of narrowband noise, and also we have seen the quadrature representation of narrowband noise. So this noise analysis will be useful in communication systems. Okay, thank you.